Hey, this is part 2 of linearity and continuity of graphs. Today we're going to focus more on looking at the equations and using that to determine if the functions are linear or nonlinear. So again, when things are in linear, written as a linear function, we know that if we was to take that equation and graph it, it would create a straight line. So when I have a linear function, it's a function whose graph is a straight line, and the domain of the function is all real numbers, and the function is continuous. A linear equation can be used to describe a linear function. So the standard form is written in this ax plus by equals c. A lot of times we see it written as y equals mx plus b. That's slope-intercept form. But it's important to know when it's in standard form, this a and b are not both 0, and a, b, and c are integers with the greatest common factor of 1. The important thing that pops out at me right off the bat is there's no exponents in there. My variables are not raised to a power higher than 1 or lower than 1. All of the variables, the x and the y here, are raised to the power of 1. That's what makes it a linear function. So a nonlinear function has a graph with a set of points that do not lie all on the same line. Maybe they're on a curve or like a parabola. And if I think about the equation of a parabola, it's ax squared plus bx plus c. So there's that squared feature in there on the x term, which makes it not be a linear function. Now it is nonlinear. So when we are looking at a nonlinear function, it can't be written as ax plus by equals c. And the function values of a linear function change at a constant rate for every equivalent change in the x values. The change in the function, this is a lot of words, so I'm not going to just keep reading it. Let's just look at it and make sense of it as we go. So linear and nonlinear functions. This, I know, right off the bat, is nonlinear. It appears so anyway. I'm looking at it like nonlinear because this has an x squared. But then when I go to this next term, let's look at what happens. If I square this 2x squared becomes 4x squared. So now I have 4x squared, take away 4x squared. Well, that's gone. So then I'm just left with this 3x minus 5, which is in fact a linear function. So be careful because they're trying to trick you, as in I told you that, the x squared makes it be nonlinear. But then when it simplifies, that x squared term totally goes away, and I'm just left with this 3x minus 5. Therefore, it is a linear function. So when I rewrite it, we can rewrite it as ax plus by equals c, moving the x term over here with the y. So I have 3x minus y equals 5. Looks like what they did was they divided everything by -1 to make this x term positive. So now it's written in the form 3x minus y equals 5, and therefore we can see that it is linear. But now looking at this one, linear or nonlinear? Of course, that's going to be nonlinear because that x is raised to a power of 2. There's nothing that it's going to cancel out with. I don't have negative 5x squared plus 5x squared to get 0. I just have a minus 5x squared. Therefore, I know that this is nonlinear because that x is raised to a power other than 1. Okay, identify linear or nonlinear. I'm going to give you a second to try this. Pause the video, just look at it and see what you come up with. Okay, so this 3x squared or cubed, take away an x cubed, leaves me with 2x cubed. As soon as I see that x cubed and it's as simplified as I can get it, I realize this is nonlinear. I cannot have a variable raised to a power other than 1 and it be a linear function. Okay, let's try another one. Oh, this is still the same thing. Last one by looking at a table. Selena kicks a soccer ball. The height of the ball after each half second is recorded in the table. The function that models the height of the ball, is it linear or nonlinear? So let's look at this. So it's going up each time by half a second. So that's good. My change in time is constant. Now let's see if the change in the y is constant. From 2 to 28, it went up by, 26? Did it go up by 26 again? No, it didn't. So my change in y isn't constant. My change in x and my change in y have to be going up at the same exact rate each time in order for it to be a linear function when I graph it. Since this is going up at a constant rate, it appears like it would be linear, but then when I look at what's happening with the y values, it's going up more rapidly. It jumps in bigger amounts and then it starts going back down. So I can see that this is a nonlinear function. Okay, example 7. Fernando uses a garden hose to fill his empty pool. The table shows the amount of water in the pool after every 5 minutes. So 5 minutes, there's 60 gallons. 10 minutes, 120. 15 minutes, 180. I see that as time increases by 5 minutes, the amount of gallons of water are increasing by 60 gallons. It's increasing 60 gallons every 5 minutes. Since this is happening at a constant rate of change, I know that it is a linear function. Again, because the change in the amount of water is constant for every equivalent interval of 5 minutes, the numbers in the table can be modeled by a linear function. If we look at the graph, boom, there it is. Every 5 minutes, it's increasing at a rate of 60 gallons, and we can see that it is a linear function. All right, and last thing I would like for you to look at, just to get you some practice, pause the video, try these problems, and after you've tried them, then unpause the video and check your answers. I don't know why this won't move. There we go. Here we go. So go ahead and pause the video. And here are the answers.